In this lecture, we're going to discuss straight line path following. So we're going to describe a straight line path mathematically. Then we're going to develop a vector field for lateral path following, i.e. we're going to be converging in the northeast plane. Then we'll develop a control for converging to the desired height. So let's see what that's going to look like. So right here we have our aircraft at its starting position, and I've designed a line. We can see that here as this red line. And we'll go ahead and once we've designed the line, then we're going to develop the control to allow this aircraft to converge to that line. So as you see, it's moving towards it. It's balancing moving directly towards it with moving along the line, and you see as it moves along as we go. So we define this line right here. We'll define the origin of the line and the line direction. We'll also define an airspeed, so that's how fast we want the aircraft to go while we're following the line. But this origin and line direction are really how we define that line, and we'll develop a vector field around it. So for example, if we wanted to change the origin to just a 200 in the x direction, we'll see that it shifts over and we're doing top down. So if we look at it top down, you see 100, 200 in the x direction. We could also have it move in the y direction. You'll see this won't actually really affect it too much at this point in time, because what we've drawn here is just a projection of the aircraft onto the line, and we moved it. We can also change the direction. So here we have the vector or the line moving in the y direction only, but we could have the line moving, diagonally in the x and y direction. Now you see a little bit of a change. So we've defined its origin at the point 200, 300. So 200, 300. So that's the line's origin right there. And we want to fly to it. So, and we've defined the direction of going 1, 1. So then if we fly to it, then this is where we'll be developing that control law. And we just have the depiction of the line moving along with the aircraft. Okay, so let's go ahead and jump on in. So you'll recall the Dubin's model for path planning that we developed in a previous lecture. And that Dubin's model, it ignores wind, assumes a coordinated turn, we have constant velocity, convergence to the command value is fast compared to the rate at which the commands are being changed. So in other words, we assume that our commands are passed through. And our commands in this case are our flight path angle and our roll. Then we said, all right, well, we can do a slightly simpler Dubin's path model where we define our position in terms of just a ground speed velocity and the cosine of our heading angle. So this is the model we're going to be utilizing more directly in this lecture to develop the path following capabilities. Okay, and then we assume that we can control height independently. So we'll utilize that. All right. So now we have a motion model that we'll consider. Let's jump into designing a path. Okay, so it just takes a few variables. One is we need to design the path to be followed, right? So this is our line. This is the path to be followed. And we define it with just a few two variables. One, we define this vector r. So this is vector we define in the inertial frame, right? So here we've just defined this vector in the inertial frame to go from the origin to a point on the line. And realistically, we call it this vector defining the initiation of the path. We could just define it as any point on the path. And then we can just say it's a point on the path. We don't care what frame it's defined in. Okay. Then we do need to define a vector q. So this is the point R, right? And we define a vector q, and this vector q is a unit vector along the path. So it just points in the correct direction. Oops. Let me highlight our path again. And I just want to write that this points in direction of path. And we'll let it be a unit vector to make math just a little bit easier. Then we have our, right here, this is our position, P. This is just the position of the aircraft. Now that's not necessary for defining the line, but for defining the following control law. Okay. From our R and Q, we can extract, so this is from the north, we can extract this angle chi sub q, which is just the course direction of the path. So we just measure it from the north axis, measure the angle to get from the north axis down to the line of the path. So this is the angle of the path. And this is in the northeast plane. So chi sub q, it's like heading where we project the line onto the northeast plane. Okay. Excellent. So then we're going to define this error vector, E sub p. So this is just an error vector from P to a point on the line. From the aircraft to a point on the line. And we're doing line following, so we don't really care how much error we have going along the direction of the aircraft. We don't care about our error in that direction of R. But what we do care is we have this lateral error. So this is the error we want to send to 0. And this is just we're going to call that the y component, where we're just saying that that's the component we're trying to squish down so that we can go down to 0. EPX, so this is, and we'll define the y and x in the next slide. But EPX, this will be helpful for getting to the right height. All right, so there you have it. We have a line defined along with some variables from the line. So these get, let me write this. So we have these two variables define the line. This variable is just the aircraft. This variable is defined from R and Q. And this variable is defined from R and P. So these are some important variables that we'll be dealing with for defining the line. But again, our line is a function of R and Q. Okay, so let's look into the lateral tracking problem, meaning that we want to, given a projection down onto northeast plane, we want to converge to this line and just keep following it. Okay, so the number one goal of this is we want to send this EPY to 0. Let me highlight that, because that That's really all we're doing with the lateral tracking problem. All right, so again, remember that EPY this is what we call the lateral tracking error. And we're going to define that in a frame that moves along that's aligned with aligned with the line. Okay, so let's define a frame. We'll call it frame P for being along this line, where, again, IP is along the projection of Q onto the northeast plane. So again, this vector right here, this is going to be in the direction of IP. So IP is going to be, IP is actually equal to Q. Okay, and we should put that probably up with IP. Okay, so, sorry, it does not equal Q. IP is equal to the projection of Q onto the line. Okay, and then our y-axis is at points in the direction of the lateral error. And to do this, we're just like our heading, we'll take our z-axis, which goes into the board, and we'll grab it and we'll rotate around it by this angle chi sub q. So this is going to be a rotation of, and I'll write it as r sub z of chi sub q. Okay, so that's where we get this guy right here. So you'll see, because we have the 1 in the z spot, we know that this is a rotation about the z-axis. Okay, so now this frame, or this transforms from, really it transforms from the vehicle to the line frame, or for vectors, we can say that it goes from the I to the inertial to the line frame. Okay, excellent. So we have this transform, and we'll be using it with vectors. So we're just going to say that it goes from the inertial to the line frame. Okay, that'll allow us to define, and we should have had a P up here. So the error in the frame P, we'll say is Px, Py, and Pz. That's just going to be equal to, we'll take our position, again, minus a point on the line. And it's important to note that it doesn't have to be any particular point. It just has to be any point that's on the line. We're going to rotate it into the P frame, and we'll call this difference, we'll call that EPX, EPY, and EPZ. So that's how we define our lateral error. So we just have that rotation matrix definition. So one thing you'll want to note, we'll use this here just on the next slide, is if we took E P dot, we'd end up getting, we would take the derivative of the first, Ri P dot times the second, plus the first times the derivative of the second, which would be Pi dot minus Ri dot. Okay, so it's important to note that the time derivative of our rotation matrix is 0. We're not moving the line, so the line is fixed. So that rotation matrix isn't going to change. So that cancels out that entire first term. And then the time derivative of r is going to be 0 as well. We'll just have a point on the line. We're not going to change it. It's just going to be fixed. Okay, so there you have it. We have this new frame where we have I sub p pointing along the projection of the line in the northeast plane. E sub p is a variable we're trying to send to 0. So this points along the j sub p axis. Okay, we're trying to send that to 0, and if we do that, then we achieve our goal of lateral tracking. All right, so let's jump into that a little bit further. So we're going to have our relative aerodynamics. This guy, and I guess I could have finished writing this. This is going to be RIP times PI dot. Sorry, I should have put the I as a superscript. Okay. Well, one thing we're doing right here is, since we're transformed, this only transforms x and y, right? So transforms x and y. So we don't necessarily care right now about any component of z. So all we care about is x and y. So our error in the x and the y direction are only going to be a function of p in the x and y direction, or p and r in the x and y direction. Okay, so if we take a look at this equation, this is just this component, of the rotation matrix. So it's the r in 2D, because we're just doing it about the z-axis, right? So we have that relationship. Let me just highlight that, because that's an important relationship. And then we have this relationship where we have pi dot, and we're only taking the first two elements of it. So we have, if you recall, Dubin's model. We have that our Pn dot is equal to just Vg cosine of our course angle, and Pe dot was equal to Vg sine of our course angle. So right here, we get the P dot in the northeast plane. Excellent. So we just have r times P dot, which is what we showed right up here on the last slide. Okay, so if we do that, so we do the multiplication and some trig, and we'll do a little bit of trig there. Then we have a nice expression for the error in the x and the y direction. Again, for now, we'll completely ignore this E sub px. We don't care how our error is growing there. What we do care about is the error in our cross-track. So we regulate the cross-track error to 0. So then what we're doing is we're trying to send that to 0. And now this second equation, the goal here is we want to design our control signal for our course angle such that EPY goes to 0. Oh, that's what we had written down there. Okay, excellent. So again, let's look at this. All we're doing then, we're not going to be changing the speed of our aircraft. All we're doing is we're just trying to change the orientation of our aircraft, right there or there. So we got to decide chi sub super c, our command course angle, such that it achieves 0 on the EPY. And you could imagine what we really want to do is have it go, we could potentially have it go straight to 0. but we don't necessarily care about doing straight to 0 because we want to go along the path. So we assume that we want to try to do something like that. So let's make it happen. What we're going to do is we're going to define a vector field. So a vector field is just it's just defining a vector for every point in space. So we have our vector field defined such that this axis is along IP, right? So if we look at the aircraft, we're pointing it, this angle is our chi minus q sub chi. So in other words, we took our, say north was pointing in this direction. This would be our chi, and this would be chi sub q. So we're saying that now we've aligned this guy right here, remember, is IP. And we can now define this angle as just chi minus chi sub q. So that's where our aircraft is. The error we're trying to minimize is right here. So this is now just defined as EPY, which we defined in the previous slide. So we have to now choose our desired course angle. So we're going to say that this, I said desired, but we're going to do a deviation. So this guy is going to be the deviation, not the desired. So keep that in mind. This is our deviation from the line course angle. This is maybe a desired deviation. So that we need to design this guy such that we can actually follow it, and that'll take us along to the path. So let's think about if we're really far away from the path, right? So here's our path angle. We're going to call this guy chi super infinity. This is the angle or the deviation from the line orientation at an infinite distance. Okay, so the question is, do we want to go? We could go directly to the line, and that would correspond to a deviation of, right, pi halves. Okay, so if we want to go directly to, if we're far away, that's a deviation of pi halves. We may not want to go all the way up to pi halves. We might want to instead, like it's shown here, have something less than pi halves. So less than pi halves will be our chi super infinity, and it's going to be greater than 0. So that way we're pointing pretty close to going towards the line, but maybe just a little bit along the line, so we are moving in the direction that we want to. But again, that is a design choice. So but remember, that's just a deviation from chi sub q at an infinite distance. Okay. So then as we get closer and closer, if we were right along, if we were at this point, we would be wanting to move right at chi sub q. All right, so we want to transition from this chi super infinity to chi sub q. So as we go over, we want to transition from chi sub infinity to chi sub q. Okay. So that's why we're going to define this desired deviation angle. Okay, we'll let it be a function of the error in the y direction, right? So the further out, the more we want to point directly at the line. The closer we are, the more we want to point along the line. So that's what this guy is doing right here. So let's dissect this, this equation right here. So this tangent inverse that we're taking, it acts as, this is known as a sigmoid function. Now we're going to switch back to blue. And a sigmoid function, all it does is it transitions nicely between -1 and +1. Well, or in this case, from a negative value to a positive value. So it's just a nice, it's a smooth transition. So if we look at this function right here, this function right here will go from -1 to 1 because we took the -π², right? Because it's at its extreme, it'd be 2/π times π². So that'd be, times -π². So go from -1 to 1. Okay, so if you're really far away, this function right here will take you from, we'll go from the -1 all the way up. If you're close, it'll be right at 0. And if you're far away in the positive direction, then it's going to be a +1. Okay. This variable right here, this just affects the slope, of the transition. So a really small value, oops, didn't draw that very well. Really small value would come out here. Ugh. It's always going to go through 0. So this would be k path small. And a really aggressive value would start its transition. There we go, I made it through the center. So this would be a k path large. Okay, so we have this sigmoid function where k path tells us that slope. Okay, so now when we take a look at the rest of this function, so if we look at this, when EPY is really big, then our desired is going to be equal to our -∞. So if we're way over here to the right of the line, then it's going to be pointing towards the line as much as we want it. Okay, or similarly, when EPY is really small, then our desired deviation is going to be up to infinity. Okay, so this is perfect. So we have the sigmoid that transitions from -1 to 1. If we're really far away, it's going to be pointing directly at the line or close to directly at the line. If we're really right on the line, then it's going to be pointing along the line. So it gives us this global feedback in terms of how we want to point the aircraft. So there's our lateral vector field. And then so the command, right, is going to be chi sub q, and we could write this as chi sub q plus chi sub d, right? Where this component right here is just chi sub d. So we have what our commanded course angle is. All right, so taking a look a little bit more at that vector field tuning, right? So, one thing, no, I didn't. That's coming up. Each row in this picture is a different value for k-path. Again, so if we have something that's aggressive, we're going to be pointing, see how this is really aggressive. Even as we get close, we're still pointing really close to our chi infinity. If we're not aggressive, this is close to, and I should have put that here, right? We still look like, even though we're only a small deviation, we're still commanding that chi infinity. And then as we get close, this is not super aggressive. We are closer to chi sub q, right? So it has a smoother transition. So if it's large, have this abrupt transition. Small, we have a long gradual. So a rule of thumb they give in the book is you can relate so if you have your minimum turning radius, you can relate k-path to your minimum turning radius. That's at least a good starting point. So the question is, right, $1 million question, does this work? And we've seen at least a video of it working, so we know that it works sometimes, right? So let's go be a little bit more thorough on that discussion. So we're going to use Lyapunov's second method, and this is something you learn in nonlinear control. So you may have not learned it yet, but let's just take let's let x be in our n, and let's define a function. Let's see, we call it v. Let's let v be a function of x, and let's let the output of that be a scalar. Okay, so if I'm going to draw this line, we're going to define this energy-like function. So I'm going to say that x is on the x-axis and then v of x. So in this case, it looks like a scalar, right? But we're going to define a function that's energy-like, where we have v coming down, kind of like a quadratic. Oh, I did almost good. And then my hand slipped. All right. So we have our v function right here. And we're going to let v be of x be greater than 0 for all x, for all x not equal to 0. Okay, so, and we're going to let v dot of x be less than 0 for all x not equal to 0. So what we can say here is that going along this first condition is if we draw a line straight across, right, given a certain value of v, there could be multiple values of x. We'll give you the same value v. So, but we can define these level sets where I'm drawing them in an increasing order, but you could also draw it decreasing, where the goal here is we want to be able to pull down to where down here at the bottom at x equals 0, we know that v of x is equal to 0. So in this case, right at this point, so if v is equal to 0, that means we know that x equals 0. This is really cool. So by evaluating by evaluating v, if v is going down to 0, we know where x is going. X is going towards 0 as well. Okay, so cool, right? So that's a Lyapunov candidate function, and then this final condition is just saying that, over time, v is going to be decreasing. So over time, if we start over on the right side, we know that we'll be going down towards that 0. Or over here, we'll be going down. So this is nice. This allows us to talk about convergence. And one thing to note here is that v dot is going to be equal to dv, the partial of v with respect to x, times the dynamics of x with respect to time, right, or our x dot. So now we can relate the dynamics of our x to this function, which helps us know where things are going. Okay. So that's a really brief overview of Lyapunov function. But if we can show that we have this Lyapunov function, then we can prove that x goes to 0 asymptotically, which is exactly what we want. We want EPY to go to 0 asymptotically, right? So we'll define this a Lyapunov function and show that EPY is going to 0. Okay, so there's right here, we define a candidate Lyapunov function. That just means that it satisfies that W of EPY is greater than or equal to 0. Okay, then we make this assumption that the course controller works and that we immediately realize our desired course command. So if we looked at this guy right here from the previous slide, this is just our course command, right? If we scroll up here, right, we have just our course command defined like we do below. Okay, so we have our course command. So in this, we're not actually evaluating our controller, but we are evaluating the vector field. So might be a tad unsatisfying because we're not taking into account the actual motion of the vehicle. All we're taking into account is if we were to be a point following this vector field exactly perfectly, would we get to that line? And the answer is yes. So in this case, we've defined a Lyapunov function, right? So W EPY is greater than or equal to 0. So that's our first condition for being a Lyapunov function. Okay. And then our second condition is that we have to be less than 0. That one's typically the harder one. It's easy to find a candidate Lyapunov function. It's a little bit harder to find an actual one. So again, remember, we're going to define this. This is just equal to the partial of W with respect to EPY times EPY dot. Okay, so we have this equality. Just so you get a good idea of where these equations come from, this is just a fun homework problem where you define the relationship down to here and down to there. So we'll allow these two things to be a fun homework problem, and we'll see that this W dot is less than 0 for EPY not equal to 0. Then that just satisfies our second condition. If we were to go back up, it satisfies that second condition, and we'll come down here. Oop, didn't mean to do that. And so we have the result that EPY goes to 0 asymptotically. So that ends our lateral tracking stability analysis. We know that if we're able to follow that course command that will then go to the line.